So welcome everybody. We're delighted to have the speaker today, Sanmi Koyejo, to speak to us today. And just a little bit about him. He's an assistant professor at University of Illinois, Urbana-Champaign. Got his PhD from University of Texas at Austin, did his post in 2013, got his postdoc, did a postdoc at Stanford. He's received numerous awards, including UAI Best Paper Award and ICHCAI Early Career Spotlight Award. I didn't realize so many different areas of his research until I started looking at his webpage and some of his papers. I know about his work in fairness, but he also has all sorts of amazing impactful work in other areas of machine learning. One of his areas is distributed and robust machine learning. Another area is applications to neuroscience and biomedical imaging, and in particular, sort of looking at probabilistic graphical models for spatiotemporal data. What he's going to talk about today is the area of, what I know. I guess it's a new area for you, but it's what I know the best, and it's his work on fairness. And he also works in, so the more general area of metric elicitation, which is the idea that in general, it's hard to know in advance and sometimes complicated to decide what metrics to use for machine learning algorithms, whether it's the loss function, whether it's which fairness metric to use. And it's a very subtle, tricky problem. And so the idea here is to develop like interactive methods that can discover experts' preferences. So it really much fits in with Schwartz Reisman's goal, where we're trying hard to combine the technology of machine learning with all of the many years of research and experience from other areas, trying to bring in human norms and experts opinions. So so he'll be talking about that today. Metric elicitation, and in particular, how it can be applied to fairness and group fairness. So I think that's all. Take it away.
Thank you, Tony. It's a very kind introduction. I will just make sure. Okay, that should be on now. Okay, so I'll get started. Thank you to SRI for inviting me. It's a real pleasure to be here. I've already had lots of great conversations, and I'm looking forward to quite a few more. The sort of breadth of expertise is, I think, quite. It's I think quite interesting, and just sort of getting a group this brought together and actually getting work done is fascinating. So I'm looking forward to, I think, some of the discussion as we move forward. So I should say, today I'm going to talk about some work we've been doing on measuring and mitigating ML unfairness. There'll be a broad framing, and then I'll dip in every few slides to sort of some of the details in the algorithms for folks who are interested in some of that stuff. And hopefully also sort of enough pointers to papers for additional details on some of the technical material. So the setup broadly is, I think now, or in the old days, we believed that data was unbiased, objective, and sort of quantitative. There's often the saying that sort of it was data, it was fully objective, and so there was no reason to sort of think carefully about exactly what we're doing because it was based on data, so it must have been fully objective. And in fact, we also believe that our algorithms were also fully objective. Again, just purely because they were based on the data. I think now we have learned a little bit more, and now we know that algorithms take on biases that we as humans have, and potentially they can make things worse in a variety of ways. And I'm hoping there'll be some fun discussion over the course of my discussion today about some of the ways that algorithms can make biases worse. Sorry, it's a bit of extra memory here. So there are lots of, I think, very compelling examples of this kind of issue. So I think one really good example is, for instance, the gender shades work that showed how accuracy differences could be, or huge accuracy differences based on existing and deployed classifiers across large established companies and sort of well-used tools. And many of us are already familiar with this work. And the key takeaway was that the difference could be up to over 30% between different groups, in particular between sort of dark females and lighter males, in terms of the accuracy of the prediction. And so papers work like this and sort of work before, work after, I think has done a really good job of disabusing us of the notion that algorithmic means sort of fair and sort of take your hands off the wheel kind of way. There are many other examples. I'll probably just highlight a couple more. Here's an example of I like as well, where there's an image classifier used for different athletes. And again, the key takeaway here, we have athletes that are playing the same sport, but when the image classifier is applied, meant to predict the sport that they're playing, is very clearly sort of biased based on what looks to be the race of the individual in the image. So the same individual, even in this case, I guess to highlight the point even more, let's say similar colored jerseys, for instance, are classified very differently. And the delusion here is that there's a lot of bias based on the race of each of these individuals. So machine learning is used more and more for important sort of decision making. And as machine learning ends up being used in these high stakes settings, I think it becomes more and more important to be sort of careful about the effects of algorithmic decisions and potentially where unfairness might lead to bad outcomes that we don't desire but don't control either. So I'm taking a quote out of this paper that says, the effects of algorithmic decisions can be indirect, long-term, not easily quantifiable, and can exacerbate existing biases. In machine learning, biases can crop up sort of all the way through the way we build systems and sort of all the way through the pipeline. So biases come up in the data based on how you sample the population. Sometimes minority groups are undersampled, or various kinds of bias samplings across groups. What you choose to measure, so the set of features that you choose to measure, can lead to bias in data collection. There can be bias in the models and computation. Typically, this is because, again, we're targeting certain kinds of problems, and we build models to be good at the problems we're targeting, and not taking into account what those models are good at might be tied to, or might be a function of some bias in the way that we're building our pipeline. Today, I'll mostly talk about measurement. So I'll talk about metrics. And I'm mostly interested here in thinking about how we decide if machine learning algorithm is fair. So this is if you build a model and you're evaluating it, what this evaluation looks like. And again, the claim is, or the statement is, across the whole pipeline, from data to models, computation to metrics, bias can sort of creep in through the whole pipeline and can cause problems all the way through. So to ground things a little bit, I'm going to talk about sort of a cartoon version of a real world example. So I'm going to take sort of loan decisions as an example. So suppose you're interested in building a machine learning model to make sort of loan decisions. And so you hire an enterprising sort of machine learning scientist, and they build you a model, and this model gets sort of 94%. And the question that you should ask yourself, and machine learners, folks who are building these models ask themselves is, sort of, are we done? Is this a good model? And in order to decide whether this is a good model, we have to measure it. So accuracy, one might imagine, is a good measure. And based on this measurement, we decide, potentially with comparison with other models, whether this model has achieved our goals, or whether we want to compare or improve on it in some way. So in this lone case, I'm gonna make the positive outcome approval and the negative outcome denial. And in this particular example, partially fictitious, suppose the false positive rate, which is sort of the fraction of times that the algorithm predicts approve when the patient, when the individual is unlikely to repay based on, say, observed data, is 90%, and false negative rate for the sort of converse case is, say, 5%. So again, we've done a bit of a deeper dive into what the model is doing. We have now some additional statistics about the model outcomes, and you can ask the same question: is this a good model? Is this a model we want to apply? Suppose we're not fully satisfied, so we try a few other models. Say we try say nearest neighbor classifier and get sort of 89% accuracy, maybe different false positive and false negative rates, maybe better and maybe worse. Suppose we try a support vector machine, another popular machine learning model, and we get another set of accuracies and sort of other classifier statistics across groups. And so the question that we need to answer before we move forward is which model we should use. So we've now tried 3 models. You can imagine trying some hundreds of models. And this is, again, common practice to try lots of different models. And each of these have different statistics, say maybe accuracy. If I drill down on various subgroups, they have different false positive, false negative behavior. They may have differences in other statistics that I might care about. Maybe accuracy across different subgroups differs. Again, the question that we need to answer in order to move forward is which model we should use. And so the way that we quantify fairness is using a metric. So in this talk and in most of the discussion, I'll think of metrics as quantifying the relative cost benefits of different kinds of errors that a model can make. This is somewhat restricted, somewhat on purpose. Again, I think that might be some fun discussion later on about expanding some of these ideas. But for the purpose of the main parts of the talk, I'll think of the metric as this quantification of relative cost benefit of different errors. And so in machine learning, particularly for classification problems, we can generally summarize the set of statistics that we care about by something known as the confusion matrix. So in binary classification, many of you might already be aware, but I'll summarize briefly. The binary classification confusion matrix is a quantification of sort of fraction of correct or incorrect predictions. So in particular, the true positives quantifies sort of the fraction of times that the model predicts 1 and the ground truth is 1. False positives and a fraction of times the model predicts 1, the ground truth is 0, and so on. So we also have false negatives and true negatives. And so these statistics are sort of the 4 statistics that we typically will measure for binary classification problem. And you can think of a metric in the binary classification case as some measurement of trade-offs between these 4 numbers. One thing that you can show, and I'll spend a little bit of time on this later, but one interesting property is that even though we have 4 numbers here, the set of possible values that you can have actually has reduced degrees of freedom. And the reason is that these are effectively probabilities, so they're estimates of probabilities. And based on the original data, the true positives and the false positives have to sum to the fraction of 1s. The false positives and true negatives have to sum to the fraction of 0s in the data set. And so the true degrees of freedom actually you can show are 2 degrees of freedom and not 4, even though they're 4 numbers. And so any 2 numbers in the confusion matrix are sufficient to quantify the trade-offs that you're interested in. In particular, if you're interested in sort of different kinds of errors and weighing what those errors, how expensive each one of these errors might be, then you might be interested in the ratio of false negatives and false positives. Or if you want to take the converse view and think about this as performance as opposed to errors, then you'd be weighing the true positives and true negatives as an example. And almost all classification metrics that we use in practice can be represented as some function of these statistics. So there are few outlier cases. They're relatively rare. Almost every classification metric used to measure the quality of machine learning classifiers are functions that look like some function applied to these classification statistics. Again, once you have the metric, you can use it to compare classifiers. You can optimize it directly. And so it's a useful, valuable measure of what's going on in your model. Just to, again, just make sure some of the basics are clear. I'm just adding here some of the common metrics that people or various folks in the community have used. Very common to have various kinds of weighted accuracy. You can also have various kinds of rates, so true positive rate, false negative rate. Many of you will be familiar with precision and recall, which can also be written in this sort of statistic type functions of statistics in this way, with a slight variation that now we have ratio functions as opposed to, say, linear functions. Another common metric is something like the F measure, which is, again, another ratio function that depends on true positives, false negatives, false positives, again, written in this as a ratio of these statistical quantities. So again, these metrics are ubiquitous for measuring classification performance across lots of settings. For fairness, we typically use a similar idea. So if you look across the algorithmic fairness literature, again, you'll find that most of the metrics, the fairness metrics, or most of the notions of fairness are built around quantifying some classifier statistic and then evaluating some notion of parity of this classifier statistic across groups. So I should caveat by saying this is somewhat specific to group fairness. And again, this is most of my discussion today. There are other notions of fairness in machine learning that don't fall as neatly into this bucket, but my discussion, all of what I'll talk about today are focused on group fairness, which is the idea that my population has a certain set of groups, potentially a majority and minority groups. And what I'm interested in when I'm solving my sort of fair learning problem is to ensure some notion of parity of some kind of statistic across the group. So I think some of the more popular ones, equality of opportunity and equalized odds and statistical parity, can all be written in this way. So statistical parity, you can think of as true positives plus false positives for a group, and then you're interested in making this equal across groups. Equalized odds, you can write as true positives and false positives as a pair, and you want this pair to be equal across groups. Equality of opportunity, you can write as true positives being equal across groups, and so forth. And accuracy as again, a very common measure of fairness. So there are lots and lots of metrics, just like in standard evaluation, there are lots of metrics. There are, again, lots and lots of metrics in fairness evaluation. I'm mostly adding this on here for additional reference if folks are interested in looking up. There's I think a quite interesting textbook from Boricus, Hartz, and Narayan on fairness and machine learning that has, I think, a quite good discussion on fairness in general, machine learning, and includes also many of the metrics that have been proposed and references and how they relate to notions of fairness that come from, say, other fields like sufficiency and independence. Another thing that has been interesting in the literature is that it became clear after a while that you couldn't sort of perfectly control the behavior of all of the statistics together. What I mean is, suppose I was interested in parity of true positives, false positives, true negatives, and false negatives. I wanted all these four values to be the same across all the different groups. If you do that, you lose a knob. And the reason is, again, classifier statistics are not arbitrarily flexible. They actually have a specific structure. So as I highlighted before, they're really sort of 2 degrees of freedom, so 2 knobs that you can tune. And if you have equality of those 2 knobs, then you just have sort of 1 degree left for safe performance that you can tune once the statistics are equal. So this has been noticed in the literature. I'll outline briefly, I think, the example that made this very clear, because I think it wasn't obvious. And there was a general hope that we could come up with a notion of fairness that was somewhat universal and perhaps sort of all of us could study and use. I think what is clear now is that that's probably not going to happen, and that fairness definitions are sort of nuanced and context dependent. And so I think the example that made this very clear was some journalism work by ProPublica in 2016. They were studying the compass algorithm, and many of you, I think, will already know about this example. And so Northpoint, who was the company developing this, developed an algorithm and evaluated or showed in when they were criticized that they had made sure to develop a fair algorithm where they define fairness based on sort of calibration, sort of equal accuracy across groups. And ProPublica evaluated false negative rate, false positive rate, and showed that Black defendants were twice as likely to be incorrectly labeled as higher risk than white defendants. And conversely, white defendants labeled low risk were far more likely to end up being charged with new offenses than Blacks with comparably low COMPAS risk score. And so what was clear from this is that there was a definition that sort of ProPublica was using. There was a definition that Northpoint was using. And those 2 definitions seem very reasonable sort of on their own in the abstract, but ended up conflicting when combined together because they conflicted in sort of the results claiming that the algorithm was fair. And so this is a fairly high profile work, I think was very useful for the field in helping to understand I think what we probably should have known earlier on, but it was, I think, really good that this made it very clear that fairness metrics in general, and this is true for classification metrics more broadly, are not exchangeable. And in fact, you can have sort of contradictory outcomes when we try to combine them. And so this brings up the question of if you're going to define fairness as I'm going to do here, which is sort of looking at statistics across groups and looking at evaluating the differences, which statistics should you look at? Because the choice of statistic and combinations of things that you look at will change your decision of whether you think the algorithm is fair or not. So this is currently an open problem. Again, as highlighted, there are lots of definitions, and again, lots of these definitions can conflict. So actually, before I move forward, are there normally questions through, or are they mostly back-ended?
I think mostly we discuss at the end, but yeah, anybody
Okay.
feel free to. I'll try to keep my eye on the chat if there's a question in between.
Thank you. All right, so I'll move forward. Feel free to interrupt me if you have questions as we go along. So I'll talk about 2 broad topics today. I'll talk about fairness metric elicitation. This is some initial work that we've been doing, I think early, and I think there's a lot of scope to improve on some of what we're working on. And our motivation is to help address this problem of selecting fairness metrics and performance trade-offs by interaction with humans. And then I'll spend maybe a little bit less time, but just briefly touch on some of the work, all the work we've been doing on mitigating unfairness, so algorithmic methods. And the primary interesting piece of this compared to existing work is thinking about intersectionality compared to some of the work that exists so far. Okay, so I'll start off with metric elicitation. So at a high level, the goal of metric elicitation is to take, in our case, say models or statistics from the models, and construct an elicitation procedure that queries an oracle. And for now, I'll make this oracle abstract, and I'll try to nail down the oracle a little bit more later in the discussion. And the idea is that the procedure creates queries for the oracle to answer, the oracle responds, and based on this interaction, the procedure can nail down some metric, some quantification of the preferences or trade-offs of the oracle. And so that's the metric elicitation problem. As you might imagine, there are a couple of interesting wrinkles when one wants to develop an algorithm like this for interacting with humans. So in particular, one of the sort of issues that we had early on is ideally the way you can do this is to query an expert with to give you, say, a numerical quantity. So I give you, say, a model, and the expert can just tell me how good is this model. And if the expert can tell you this for a variety of models, then you can imagine this is just a regression problem, and you can come up with fairly simple approaches to maybe interpolate and use this to quantify, to elicit preferences from the expert. There's still technical issues, but in many ways, this is somewhat easier problem than what we think is maybe slightly more appropriate. So we focus on pairwise comparisons. So the idea here is that the experts may not be able to give us query responses for individual queries, but may be able to compare quantities and give us preferences between those quantities. The other knob that that's important here is we're interested in quantifying how many queries we need to nail down the metric, because lots of, in sort of real world settings, fatigue is a non-trivial issue. If you have queries that require sort of long interactions, it can cause problems in sort of data collection and fatigue from the participants. And so we're also interested in making sure that we can do this with sort of as few queries as we can get away with. And so most of what I'll talk about today on the algorithmic side is some work trying to quantify how sort of number of queries interacts with the quality of the results that we can get. So in terms of what these queries actually looks like, I should caveat by saying our sort of initial work on this started on the algorithmic side, and we're sort of going closer and closer to real evaluation as we're learning more about the problem. I say that to say that I think there's a interesting HCI problem that we have not, human-computer interaction problem, that we have not fully solved, and that's asking the question of sort of precisely what the best ways are for querying the oracles, the users, the experts. But there is a variety of existing work that we are building on in some of our initial real-world evaluation, where there is some literature looking at how to compare, how to visualize, say, confusion statistics or other sort of model statistics and compare between them and elicit preferences between them. So ways to visualize or show to users or experts confusion statistics so that they can pick which ones they would prefer. And so the idea, and where we will eventually get to, is that our goal would be to show users or experts pairs of these statistics, and based on these statistics across models, we can try to nail down what the trade-offs are between the different kinds of errors that the model can make. I should also mention that you can also do something very similar using examples instead of using the confusion matrices. The key idea there is that we know how to map back and forth between the classifier statistics and sort of the classifiers that achieve those statistics. And so you can sample examples and then show users different predictions across subsets of examples. This idea also allows you to do populations of users instead of a single user. And the idea here is now you would get sort of average preference results as opposed to sort of a single preference outcome from a single oracle. So again, this is early days in terms of the HCI angle on this. Most of what I'll talk about today are the algorithmic results, where we're trying to understand how to do this efficiently and sort of some of what we can try to answer, particularly in this talk in the fairness space. Okay, so I'll talk a bit about recent work on group fairness. Before I move forward, I'll also say that for this problem, we are using rate statistics and not the confusion matrices directly. So the rate statistics would be true positives and true positive rate and true negative rate. As I talked about at the beginning, false positive, false negative rate is similar. I'll explain in a second why we do this. It turns out to make the problem, it turns out to be an important sort of geometrical, it turns out to lead to important geometrical properties that we use in the elicitation algorithm. So I've mostly talked about binary classifiers to keep things simple, but I'll shift gears in a second to multiclass. So in multiclass classifiers, the algorithm can predict up to k classes instead of just the binary yes, no. It can predict 1 through k. And the ground truth label can also be 1 through k. And now the set of possible statistics are a bit richer. Instead of being just 4 values with 2 degrees of freedom, it's now k-squared values. So 1 value, 1 statistic for every ground truth and classifier prediction pair. So it's a bit of a richer space, but the same intuition and the same sort of key ideas exactly roll over from the binary case and multiclass case. The multiclass case is, well, I decided to, I guess, describe the result in the slightly more general setting of multiclass, but the same thing again will work for both binary and multiclass. Again, we use rates instead of the confusion statistics directly. So it's just the value divided by the column sum, which reduces degree of freedom. So a bit of notation. So this is my first very short deep dive into some detail. So if I give you a classifier, then I can define the rate statistics. The degrees of freedom are sort of k-squared minus k. So it's, again, more restricted than all k-squared values. And you can also do this not just for the overall confusion, but like before, you can do this for every group. And so if you have m groups, then you have m rates vectors. This is potentially quite big. In the binary case with 2 groups, it's small, it's sort of 2 times 2. But in the most general case, it's sort of number of groups times the degrees of freedom in the confusion matrix. So it's a bit of setup notation. So given these rate statistics, I can define a fairness violation. And this fairness violation is measuring the discrepancy between 2 groups, U and V. So it's the difference between the rate statistics of group U and the rate statistics of group V. And because we care about violations in both directions, so whether RU is bigger than RV or RV is bigger than RU, we have an absolute value to sort of capture the pairwise notion. So violation in both directions. Okay, with these definitions, I can sort of describe the overall metric. So I'll walk through terms. It's a little bit detailed. So the first term is, or this term is the sort of utility measure. So this is measuring an extension. If you think, you could think about it as a generalization of accuracy, but this allows reweighting different kinds of measures. So I guess weighted accuracy instead of regular accuracy. Sorry, I tongue-tied for a second there. So you can think about this as weighted accuracy, which allows you to, again, in the overall performance, if your utility is larger for certain kinds, subsets of classes, for instance, this allows you to quantify that. So it's again, just generalization of, say, weighted binary accuracy to multi-class settings. On the fairness side, we have this discrepancy we just defined. And to allow for full generality, we allow this discrepancy to also be weighted. So you can have a weight for every pair of groups. You just need, I guess, you don't need all sort of m squared pairs. You just need just the combinations. And so you end up with a term for utility, a term for sort of average accuracy, average across all the groups, and a trade-off term that tells you your trade-off between the performance measure and the fairness measure. So we chose this definition because it's very general, as you can see. In particular, it captures all of the fairness measures I've talked about so far. So it captures equal opportunity, statistical parity, accuracy. All of these you can write as special cases of this definition. It also captures utility functions that can be more general than standard accuracy. So if you have a utility that's more general and you have a sort of fairness discrepancy measure that's more general, all of those would be special cases of this framework. So this is useful because then we can set up our elicitation problem as a generalized elicitation such that sort of if the metric of interest is one of the existing classes, we can recover it. But it also has additional flexibility to allow you to model other notions of trade-offs that are beyond the existing definitions that are popular today. A little bit of extra nuance. So lambda, the trade-off term, is between 0 and 1. Metrics are scale invariant. So if I take a performance metric and I multiply it by a value, it's the same metric because any classifier I evaluate it with, if I evaluate 10 classifiers with it, they're ordered the same way in terms of performance. So the scale doesn't matter. They're also sort of invariant to additive shifts, again, because we're using the metric to measure performance and like order different models. And so because of these two invariances, we can enforce that the norm of the weights is 1 for both the utility weights and the fairness mitigation weights. So that's a little bit of extra nuance there. Okay, so I've set up the problem. The problem is still reasonably complicated. It turns out that you can easily show that sort of the overall rates which you're using for the utility portion of this is correlated with the group-specific rates which you're using for the fairness discrepancy, which makes the elicitation on its face a little bit challenging. As I mentioned earlier, you need to think about both positive and negative fairness violations. And so the metric is nonlinear. And so linear elicitation is a little bit easier. We have some existing work on this. The nonlinearity makes it somewhat more challenging. It's also true that sort of as you increase number of groups, you increase the number of parameters you need to estimate because sort of the B scales with the number of groups. So that increases scale, query complexity to some extent. At the end, I'll talk a bit about ways that we can make additional assumptions and maybe restrict things a bit, but I'll defer to results before I go through those details. So before going into the algorithm, I wanted to go through an experiment that we did to see, to evaluate the usefulness of this approach. So we set up a simulated experiment where we had oracles that had some sort of predefined, pre-selected fair metrics. So there's metrics that have this general form as described here, where the B's and the A's and lambdas are, for this situation, we just sampled them randomly. And again, what we're interested in is what these metrics do when we apply them to machine learning models. So we trained 100 different classifiers on these 4 data sets. These are reasonably standard sort of benchmark data sets in the machine learning literature for looking at sort of fairness problems. And what we then did is we evaluated both the elicitation procedure for each one of these data sets, for each one of these oracles, compared to quote unquote naive approach that just equally weights everything. So on the accuracy side, on the utility side, it just uses accuracy. On the fairness side, it just has sort of equal weights on all the possible discrepancies. So you can think about this as sort of trying to make everything equal. And then the trade-off term was set to 0.5. So this is our quote unquote sort of naive approach. We also compared it to a metric that doesn't have fairness at all built in. So the metric that only looks at accuracy or predictive performance. And so the idea of this experiment is to compare if I run this elicitation procedure against this simulated oracle, and I compare it to not running the elicitation, does it actually make a difference? So does this elicitation procedure lead to different ranking of classifiers? Like, do you pick the right classifier more often if I use the sort of elicited or true metric compared to using what you might do right now, which is some default notion of either performance or of fairness measure. And so here are some results. The way that we evaluated the results are using ranking measures. The paper has additional results looking at the elicitation itself and seeing what the quality of the elicitation is. And I'll talk a bit about sort of guarantees that we can give in this setting. The main takeaway a few takeaways that I want to highlight here is one observation is that the elicited metric always correctly ranks the classifiers. So it correctly picks sort of the classifier that best matches the metric as the best one and sort of orders all the classifiers appropriately. Even when it has errors in the elicitation, it gets the ranking right. This is important because, again, remember that the way we use metrics in machine learning are to select models. And so what you care about is that the metric puts the sort of best model at the top. And so this is checking exactly that.
Can I interrupt for 1 second, Sammy?
Yeah, please.
I'm a little bit confused about when you say elicitations. Can you say a little bit more about how, who's being elicited and what you said pairwise preferences that they're expressing, but it wasn't clear to me exactly how those pairwise preferences are. What are they ranking, and how does that fit into your objective?
Okay, so the goal is to elicit a metric of this form.
Right.
The measures that are being compared are I have this coming up in a second, but I think it's a good thing to mention here and clarify. So what we want is to be able to query an oracle with pairs of rate statistics. As I mentioned earlier, this can be done directly using direct comparison of classifier statistics, or can be done directly by converting these into models and doing comparisons over predictions from those models. Based on those comparisons, the oracle tells us their preference, and that's the only signal that we get from the oracle. And what we want to do is construct a sequence of pairwise preference queries such that we can nail down, in this setting, we want to nail down A and B and lambda. So
in terms of the elicitation, it's not an elicitation of individuals or experts. You're saying it's an elicitation of with respect to an oracle, is that right?
So the oracle is a stand-in for individuals or experts. It's any, the key thing is that we can query the oracle with pairwise to get pairwise preferences.
I see. Okay.
Yeah, so I think there's another question or comment somewhere.
There was a comment in the chat.
Oh, okay.
Saying proof of concept.
Yeah, proof of concept. Yeah, so hopefully that clarifies the definitions here. The other piece of this was what the ranking is doing. So we start with a true metric, which is fixed. Then we train a bunch of models. The models either trained to optimize. Actually, the models are just trained by themselves. So we just trained but by tweaking different hyperparameters and things like that. And we're trying to, the thing we're simulating here is a machine learning pipeline where you are taking a bunch of models, you're evaluating them, and the thing that you want to make sure is that your metric puts the best model at the top, the next best model is the second one, the next best model. So it ranks the set of models appropriately because, again, we use metrics to select good models. And so what we want is that the metric sort of correctly ranks the quality of the different models. So that's the sort of simulated test that we're targeting here. And so we compared using accuracy alone. So I take my set of models, I just compare the accuracy, and I rank all the models by accuracy. The second approach is we have a quote unquote naive, if you like, call it a default fairness metric. So this uses accuracy plus uniform weights for all violations. And then we get a ranking of all classifiers using that metric. We have 100 classifiers here in this setting. And then we also run a elicitation procedure for Oracle that simulates the true metric. And then we rank all the models with our estimate of the true metric, where the metric is, again, sort of something in this family. Does that answer your question? Yeah.
I was going to ask a follow-up question. So is the goal of the experiment to see if the different models, linear regression and so on, if different ones give different, become higher or lower up, depending on the metric that's selected?
Yes. So it's targeted answering the question sort of, does metric selection actually matter? So I think it's often assumed that so if I target high accuracy, that's all I need to do. In this context, it may be a bit of a cartoon, but we've actually had to argue this quite a few times. So I think I guess that's the reason I'm bringing it up here. So it's showing that using the sort of correct metric changes what model I would pick as the best model. That's I think the primary takeaway. We're doing this for the entire ranking, not just the top. But again, these models are arbitrary, so you want sort of good selection to persist across the whole list, ideally. Does that answer your question? Okay, thanks. Okay, so again, the three things that we're comparing is the elicited approach, which tries to get the true metric, the equal weights method, which is sort of a default fairness and accuracy measure, and then one that only looks at predictive performance and doesn't care about the fairness measure at all. And again, the key takeaway is that using the elicited metric always ranks the different classifiers the right way. So always correctly ranks all different models. Using equal weights sometimes does pretty well, though can be a little bit off. And only optimizing for accuracy in this sort of simulated example does the worst in all our experiments. Okay, so let me dig a bit into exactly how we do this, because I think that's also interesting. So the main idea that enables this elicitation is exploiting some geometric properties of group statistics. So if you look at the set of classifier statistics across groups, it turns out that they have some interesting geometry that may not be obvious from the outset. So in particular, you can show that the rate statistics across classifiers are the set of rate statistics actually are, you can show that they're convex sets. You can show that they're convex set with vertices that correspond to making random decisions. So if I take a randomized classifier and I apply it to a group, I'm gonna get sort of a trivial rate vector. In particular, because rates are normalized confusion statistics, you can show that this will be sort of 1 in one location and then 0 everywhere else. And you can show that these vertices are shared across all the different groups. All groups have the same vertices, even though the shape of the group confusion can be, the shape of the group statistics can be different. There's always some point that corresponds to a completely random classifier that is again shared by all the different groups. And what this ends up being useful for is that you can always embed a sphere. So if I map out the set of all rate statistics, I can always embed a sphere within this set. This ends up being very useful. Again, I'll talk about this a little bit more in a second. But the intuition that I want to get across is I take some sort of data distribution or real data. I compute classifier rates for all possible classifiers or some large set of classifiers. I look at what this set looks like. So I sort of, if I want to visualize the set of all possible rates, the claim again is that this set of rates has some interesting geometry that is maybe not completely obvious, but ends up being very useful. And this geometry is what we end up exploiting for the elicitation procedure. So in particular, if I just give you the sphere of rates, and I'm interested in linear metric. So this is a metric that just weights each rate statistic with some value. So I want sort of bigger values for the rates I care more about, smaller values for the rates I care less about. The trick that I can play is I can embed this sphere essentially in a plane. So I can expand this sphere into a plane by quadrants. And so we do exactly this. So I take the sphere, I take an orthant of the sphere, which is a set of rates corresponding to sort of, so within the set of feasible rates, I have the sphere of sort of a subset of rates that I'm interested in. I'm realizing now that without some of the context, this is not working as well as I would like. Sorry, I normally have a lot more detail. Let me go through the key ideas, and maybe I'll add context if needed later on. So the key idea here is that I can take the sphere, this embedded sphere, I can expand it out into a plane. In particular, we can do it dimension by dimension. And so the trick you can play is that I can do a binary search. And to answer the question earlier of exactly what this elicitation looks like is, I'm interested in finding the maximum point of this curve. And this curve, every value in this curve is a possible rate vector in the inputs. The output is the sort of the performance of sort of how good this rate vector is as evaluated by the oracle. What I'm able to do is compare pairs of statistics. So I ask the classifier, is theta A better than theta B, yes or no? Is theta B better than theta C, yes or no? Theta C better than theta D? Each of these thetas corresponds to a rate statistic. Each of these rate statistics corresponds to a classifier. So I can ask the classifier to compare. So I can ask the oracle to compare classifiers. So the oracle sees classifiers and is comparing them. We convert it into angles and are comparing angles. And based on our angle comparison, we can pinpoint in every dimension what the maximum statistic is. This maximum statistic can then be converted into the metric because this maximum statistic identifies the point on the sphere. This point on the sphere, because it's a convex set, has a tangent. And this tangent can be described by this line A. So a bit convoluted, but to summarize, we're interested in finding the best linear metric in this simple setting. The best linear metric corresponds to a line, which measures the quality of any possible rate statistic across all the ones that we could compare. We convert this line into finding the best point on the sphere. In order to query the oracle, we ask them sort of pairwise comparison queries. How good is this race statistic versus another one? This comparison on our end looks like comparisons of angles. And simple binary search allows you to find the best angle. And once you know the best angle, you know the best rate statistic, you convert it back into getting the best, the associated linear metric. Up to scale, and so remember these, the elicitation procedure, linear metrics, or any metric is known up to additive affine transformation. So up to a scaling and sort of adding or removing values, I can identify what the sort of best linear metric is. Okay, so that's this is work that we had done before when we're interested in eliciting linear metrics. This will turn out to be useful as a subroutine in the sort of general problem of eliciting fairness metrics. So I wanted to go over it just to set up the subroutine. If this sort of was sufficient description, you can go with it. If it's not, I think it's also fine. I think the rest will be okay. You should see this as a subroutine that lets you elicit a linear metric, and we have some sense of guarantees of how good this can work. And what I'm going to show over the next couple of slides is how we can convert the fairness metric elicitation problem into a sequence of linear metric elicitation problems, and use the linear metric elicitation problem as a subroutine to solve this larger, more complicated problem. Okay, so the first thing we're going to do is, so we're going to break up the problem into 3 parts. We're going to elicit the misclassification cost, the utility function. We'll elicit the fairness metric, and then we'll elicit the trade-off. And so these are the 3 parts of the elicitation procedure. For the first part, on all of these, we'll exploit, again, this geometry of rate statistics, which will make sort of the problem, essentially, most of the work is on the geometry side. Once we understand the geometrical properties, the elicitation procedures are variations of binary search. So from the oracle's point of view, it's making pairwise preferences. These are essentially effectively underneath the hood binary search algorithms, and this is what we need in order to sort of pinpoint the metric. Okay, so the first thing that we do is we're interested in eliciting the misclassification cost. The property that we exploit is if I can restrict my search to, again, this sphere that's embedded within all the different rate statistics measures. And within that sphere, all of the original metric, actually, the fairness measures are not active within the sphere. And the reason is that, again, I'm within the sphere, so all of the classifiers, I've set up the problem so that all of the groups have the same statistics. So if I restrict all the groups to have the same statistics, I want to know what the trade-off will look like from the oracle. Once I do this, and the way I do this is that the way I query the oracle now is I ask the oracle queries that look like just repeated queries across all the different groups. So there's no notion of group difference when I'm querying the oracle anymore. Once I do this, the metric looks like a linear metric. And so the oracle just needs to answer sort of standard linear metric queries. And once they do this, this gives me this A value. So this gives me the sort of misclassification cost / utility function value. The next step is eliciting the fairness violation. This is a little bit trickier. The way we do this is, again, we do a bit of manipulation to fix trivial groups for some sets of classifiers. And again, what this does is it linearizes the problem. And so once we've linearized the problem, in this simple case, suppose we had just 2 groups. So if linearize the problem for the 2 groups, we can run the linear elicitation procedure across those 2 groups. If you look at the form of this, this ends up being a linear problem. Once we're done, we just solve a linear system of equations to identify B for this pair. If you have more than 2 groups, you can partition recursively and repeat the sort of algorithm m times. And once you're done, you've elicited, you have A from the previous step, and now you've elicited B as well, which is this fairness violation weight. And then the final step is to elicit the trade-off. And to do this, again, we'll linearize. So we exploit the fact that I can rewrite the problem by just looking at one of the groups and ignoring the other. So I have a trivial prediction, all the groups except one. This again linearizes the problem, and I just use a simple binary search to find the trade-off. So, so taken together, we have a sort of three-step process. In the first step, we elicit just the sort of trade-off term, the accuracy term, which is telling us the utility. In the second step, we elicit the violation, the fairness violation term. The first step requires querying at least as many times as entries in A, because again, remember we're looking at rate statistics across K classifiers, so there are K squared possibilities for the different weights. So this needs at least that many order queries. Similar things for the fairness violation. There are K squared possible comparisons for the K classifiers, and then their M groups. And then sort of order constant queries for the trade-off term. So once we're done with this, we've identified the utility function, the trade-off, and then the fairness violation weight. Okay.
Just 1 second. So I wanted to just mention that we usually like to leave some time for discussion. I wasn't sure if it would be possible.
I am a little bit over. I'll skip most of the. Go ahead.
You know, I was going to say you're welcome to keep going for a little bit longer, but it's about 5:04 now. So
yeah, give me 1 second.
Thanks.
So I was going to. I guess I don't need to hide this. So I can just go to discussion and maybe start some of the discussion. So yeah. So I think there's some interesting, just to get things started, I'm sure there'll be additional questions. So most of what I talked about today are sort of a little bit in the weeds in retrospect, but some details on how we elicit group fairness measures. I think there's a interesting set of questions about whether we should be trying to quantify fairness. I would argue that it's useful, but again, I think this is discussion time. So it, of course, is tricky, but I think it's a useful thing to try to do. And I've discussed our sort of initial steps in trying to do this. The other question I think is interesting and we don't have perfect answers for is this question of who exactly should you be querying? So we formalized the problem in a somewhat abstract way. Our initial applications are focused on settings where it's a little bit more obvious who might be good oracles to query. So we've been looking at healthcare applications where the medical experts, I think, are maybe the obvious query folks, oracles to query. But I think in general settings, it's maybe trickier on sort of whose notion of fairness should be the important notion of fairness. One property that I think is useful from our approach is that even if this approach is not used, or this general framework is not used to define the fairness measure, it's useful for surfacing sort of the trade-offs that are being made by the oracle. So it quantifies sort of intuition into numbers. And I think the surfacing can be useful just for sort of understanding what's going on. So what trade-offs you must be making if you have these sets of preferences. But I think it's a very open question, and I think it's one that we haven't fully answered in a general way. Yeah, okay. I'm happy to share slides. Again, I maybe even extend the slides. I think I tried to do a bit too much in a short time.
Yeah, thank you so much. So let's take some questions. Does anybody, if you have a question, you can put in the chat or just speak right up. Well, I'll ask some questions that
Okay.
give you some time to think. So just one thing, what is Goodhart's law?
So it's, sorry, I should have mentioned that. It's, I guess it's the idea that once a measure becomes a target, it ceases to be a good measure because sort of then you over optimize for it, and essentially you'll find the loopholes in the measure once you've defined it. And so it advocates for sort of being careful about selecting measures because you're susceptible to that particular bias.
Okay, and then another question that I imagine a bunch of people are thinking, I certainly am, is like, to me, a big issue is that you have different people that, you know, it's like a game theory setup. You have different people with different preferences, and you know, they're going to be probably competing or conflicting with one another. So have you thought about how to, how to set
A
that?
little bit. So I think the approach that we have now is somewhat limited in that it can handle a single oracle or average preference across a set of oracles. It doesn't handle, I guess, wide discrepancy across oracles in a graceful way. Essentially treats each user as an ID sort of independent sample of a population of users, and we're interested in sort of the average preferences across the group. I think there's a lot of scope to think more carefully about what to do across groups that, as you said, might be conflicting, and what we should be measuring, and sort of how we should be aggregating their preferences together.
Interested in, back to the ProPublica, I'm even interested to know if that data, if, you know, both groups claimed that they were optimizing different metrics, I guess they, and then, you know, even with that specific data, what's, if you did the same experiment on that, would you see much difference in models, and how can one decide which of those two metrics in that specific case?
So again, I think I don't know that you get a good answer to that question, because I think the key takeaway again is that it's context specific. It's sort of the oracle determines what they think. So it really does depend on like who you are querying for the preference, or the population that you're querying for the preference. So if you ask the question that you just sort of outlined, if you change the set of individuals, so if you asked, I guess, the North Point folks, they might end up with their own metric, and the ProPublica folks will end up with a different metric, and they will be likely different because it's a different group, and they have potentially different trade-offs of what they think fairness means.
I mean, I guess one thing good is you're forcing them just to state it up front.
So I think that's a good, yes.
After the fact.
Yeah, so this is useful in cases, I think it's definitely a non-trivial issue of sort of, I guess, how you deploy something like this in practice. I do think the sort of forcing to state up front is a potentially big win. I think when it is clear what the stakeholders should be, and which again is some subset of fairness settings, I think it's quite clear, then I think this directly is useful if average performance or average measures over the stakeholders is the right notion. Beyond that, I think maybe there's still some more work that we have to do to, again, think of aggregation in more general settings and what trade-offs might look like across individuals to better answer the question for sort of slightly more general settings.
Thanks.
Yeah.
Whoever would like to, anybody has comments, questions.
One question about, so you said that all this is about group fairness. In some sense, I would think that if you're doing eliciting from experts, the question is whether, so preference elicitation more naturally may be done on an individual basis, right? So taking an individual descriptions of individuals and saying, you know, was this fair, or comparing individuals and the kinds of treatments they got. So it seems that there's a natural fit of elicitation to individual notions of fairness rather than group. I wanted to see what you thought about that.
Yeah. So I should say, I guess, our motivation. So there is already a bit of work on maybe how to select or interact with experts for coming up with, in individual fairness, the main issue is your notion of comparison. So who are similar individuals? And there's a little bit of work out there already on how to try to approach this problem. It's not obvious to me that it's maybe more natural in the comparison sense, because I guess we hope that people can compare individuals more easily. I think there's a larger question of notion of fairness that is also tricky to answer. So if you like, there are two levels, right? There's a level of which notion of fairness should you use, and then given the notion, what actual measure should you use? I think we started from, suppose you're interested in group measures. How do I pick a good group measure? I think it's completely valid to ask if you're interested in individual, then how do you pick a good individual measure? Or the meta question of should you use individual or group? I think that's also interesting. Group seems very useful for particularly policy applications, and I think many sort of policymakers like to think in group terms. So also a lot of our initial sort of motivation started out from group fairness settings. So I guess and from that point of view, it was the natural way to think about it. But I think, yeah, to your point, one could also, and there is work thinking about individual versions and how to pick a notion of similarity. The problems are not interchangeable, unfortunately, at least as far as we know, both in measures themselves or also in elicitation. So, the distance metric doesn't naturally translate into the fairness measure, or vice versa. So they seem distinct, at least the ways that we phrased and are looking at them.
Thanks.
I'm okay. I'm gonna start talking, even though I see someone else has unmuted themselves. Now, I'm trying to understand something quite early on in your thought process, or in this work, which is with the accuracy-based definitions of fairness. So you have these fairness models, but they're all about trade-offs between things like false positives and false negatives and so on. And it makes it is intuitive that when you have group-based differences in, say, the false positive rate on some decision-making program, that can be unfair. That does seem to me like a kind of unfairness. I'm curious, though, if because lots of decisions that we might want to use algorithms to make don't have there's not a ground what's the word you use, ground fact of the matter, of how, especially where fairness is concerned, right? Moral decisions don't have a fact of the matter that with respect to which we can assess accuracy. I'm wondering if that ground truth, thank you. I'm wondering if that if that makes those kinds of decisions just totally outside of the scope of this work, or not. And more generally, I'm concerned about your approach here, because it seems to me like the space you're working in, you're kind of minimizing the distances in a complex multidimensional space, and that's those distances are the differences between sort of perfect accuracy and the various measures of accuracy of your particular metric. And my issue is, although I think it is true, intuitively correct, that it's unfair if, say, the false positive rate is way higher in one group than in another, it's not clear to me that moving in that space is the same as moving towards fairness, because fairness is a different space. And this kind of problem, if that is a problem, would only be exacerbated when you try to combine different experts as oracles. And this is a problem with a preference aggregation that I think is kind of well studied in public choice theory. Like people have different preferences, but then the preferences don't exist in the same space. So if you try to sort of average them, you can get to nonsense instead of getting to some kind of group notion of fairness. So it's kind of a question about generalizability, and then also a concern with the overall approach, which perhaps you can assuage me with.
Yeah, that's I think interesting question. So to the first point, which is that we're looking at the statistics, and the statistics might not be, I guess, the right notions. Well, it's not clear what statistics on each one on their own. Thinking of equalizing them makes sense potentially. But it's not completely clear that sort of which or how or so what combination of things is a good definition of fairness, if I understood the first part of your question correctly. If that is true, again, that's where we're starting from as well. So I think the thing that we're taking as a given, which I think is a fair criticism, is that we're starting from the fact that sort of your range of fairness measures is within the space that we're looking in. And if it's not, then what we end up getting is sort of our best approximation to the range of fairness measures. I think that's a very fair criticism. And in fact, I think the way forward in that direction is to make the space richer, richer and richer. I didn't go in a lot of detail, but the algorithm itself is reasonably general. So one could imagine adding additional features and still being able to use the same procedure that I sort of glossed over to solve it. So, but let's say we restrict ourselves to just these sort of race statistics. So these things that are capturing classifier confusion trade-offs, and sort of asking to what extent we want parity across these values across different groups. So again, I think the arguments, well, I'll argue two ways. One, maybe a bit reductionist, but everything that's out there looks like something like this. So the argument is maybe that we're not looking in the right space as a whole community. I think that's potentially valid. But if you buy that we may be in the right space in terms of, at least we're looking at useful quantities, but we don't know how to quantify trade-offs between them, then I think our approach is useful because it helps you pin down those trade-offs. If you think the quantities themselves are not useful or not rich enough, then I think the work is maybe extending what those quantities are. So the things that you're comparing, right? If you think you should be comparing additional things. And I strongly agree that I'll just restrict myself to machine learning, but machine learning tends to be reductionist, particularly when applied to individuals, right? You convert people into a set of numbers, and anything that's not, in that box is discarded. That's the only thing that's the measurement part. And sort of mistakes that you make at that point will persist. And so if you don't measure aspects that are important, they'll sort of, you're not going to fix it, at least not in a straightforward way later on. I guess broadly, I'd argue that sort of if you take the framing that's current framing, I think we're making a useful contribution in terms of helping quantify trade-offs within that framing. And the approach can be generalized to additional sort of framings that are, again, comparing statistics across groups. If you don't like the statistics view and you want sort of other ways of thinking about what fairness might mean, you alluded to sort of parity in those statistics is not fairness. Again, I think fairness is a complicated term and has different meanings to different individuals. And so one example is, again, you could consider instead the individual fairness measures that we were just discussing a second ago, which is a completely different class of potential fairness measures that is mostly tailored to thinking about, it tries to focus on similar individuals to be treated similarly as opposed to groups should be treated similarly. And you end up with slightly different, somewhat different results. To your last point, which was about aggregation across experts, potentially quite differing experts. I completely concede. I think that's something that I think that's maybe one of the directions that I'm hoping to make the progress on, hopefully soon. So again, our approach is simplistic when it comes to aggregation. It visualizes an oracle as an abstract object, and the way that we interact with it is sort of sampling from it. And so if you have, if your oracles are very different and what you care about is not sort of average preference, then our approach as is will not work. If both of those things are true, then it's fine. If it's not, then some of the work that we're trying to do is, again, thinking about richer, more nuanced notions of aggregation. That hopefully answered your question, or partially.
Thanks.
So I'm curious if you wouldn't mind expanding on that, excuse me, that last point a bit. So just, I'm trying to understand whether we need a model of like a fairness aware model of the oracles themselves to get the aggregation right in the case where oracles might have different behaviors. Like I really like the way the work sidesteps the need to pinpoint the fairness metric itself and then uses the oracle feedback as a way to search this space and negotiate the trade-off. I'm wondering if there's a limitation and whether we need to somehow model bias that might sneak into the process through the oracles, and if that's the case, whether a fairness metric is needed to do that, or if there's other ways we could think about doing that. So like optimizing over the worst case oracle in sort of a minimax way or something like that.
Yeah, I think, well, you sort of answered your own question, so thank you. I think in some ways, maybe it pushes the can a bit, but it's not clear that there's an alternative. If there isn't a single oracle, then you need to reason about how you want to aggregate preferences across the different oracles. And again, like I said, we make the simplistic assumption that you're sort of, that average aggregation is reasonable. I think notions of aggregation should themselves, I think, worth study and have a non-trivial effect, I guess, on what you think a good result should be. So I think there was some earlier discussion I had, again, folks who think about preferences in economics and voting have a lot of history thinking about what aggregation looks like across different preferences, and sort of the whole Arras theorem about fairness in voting situations that suggests that it's tricky in many ways. I don't know that we can get around that problem here either. I think if you wanted to reason about aggregation, as I think we should, then you have to, I think you have to, as far as I know, you'd have to decide what your notion of aggregation is. So what is the social good? What is the sort of combined best behavior? Which could be min-max, like you said. It could be average, like we can already handle. It could be some other weighting itself. But in some ways, this is a meta question. It itself needs to be answered. It's not clear that, I guess, one can elicit that meta level, because then you have an oracle that's deciding the weighting, which again doesn't seem to have answered the question. So yeah, Yeah, it's an interesting, tricky question of what the best way, what's the best way to combine preferences that may disagree with each other. I don't know yet, and I don't have an obvious answer. We're hoping to play with variations on aggregation schemes that exist in economics for now, to think about at least more nuanced directions. But I don't know that there might be a clean algorithmic framework to think about that. Or general, I guess is the right word.
Well, thank you very much. I join everybody to thank Sanmi with me. It was a great talk. And yeah, it's lots of hard questions here to be left to discover. But thanks again. It was a really great, thought-provoking hour and a half.
Yeah, it was a pleasure. Thank you for having me. I appreciate it.
Great. Okay, and I think you said you could have your slides available, so if anybody wants them.
Yes, I'll. Do I just send them to you?
That would be fine. Yeah.
Okay, sounds good.
Okay, great. Thanks, everybody. See you next week. Bye.